All right. Hello, everybody. Welcome to the class. So we are almost reaching towards the end of our course. Uh, we'll be covering topics on clustering today. Clustering is very well known. There you go, screenshot. Yeah, clustering is something that a lot of people who have not done data science or machine learning also sometimes hear about. I'm not sure how, but for some reason it's a very popular paradigm or set of techniques. So the idea, to keep it very simple, like a cartoon idea, is given a bunch of data records. The idea of clustering is to just group the records into different groups where the records which fall into any given group are similar. This falls under a paradigm called unsupervised machine learning. So all you did till now with random forests, SVM, everything is supervised machine learning, right? Because you're trying to take a bunch of input records, and you also have one specific column that is, say, this column, that is your label. So say all these three columns are your input variables. You can have, of course, hundreds of input columns. Then there is going to be one column which in classification problem, you will have a label, like for example, spam or no spam, fraud or no fraud for each record, right? You have a lot of records of data, right? Maybe 100,000 records, 3 variables, or maybe 300 variables, 3,000, whatever it is. You have one variable always known as the label variable, which has the ground truth of what class or bucket it belongs to. And that's what you want to build a model, so that in the future, when you get only the input variables, you'll be able to predict or classify the output variables. So that's the classification. Similarly, in regression, you have a real number here. Instead of a category, you have a number. So trying to predict crime rate or housing prices, stock prices, all this is regression problems. So regression and classification, it is supervised learning. You have input variables, you have output variable provided to you. In clustering, you don't have an output variable. All you have is all variables are input variables only. So this is unsupervised learning. You don't have a target to predict. You don't have a target variable to predict or classify. And you also don't know what the ground truth is. So say I give you a bunch of emails and I don't tell you for your training data which email is spam, which email is no spam. So your data already has spam and no spam mixed in it, but you don't know which one is what. If that is where you're starting, then the paradigm is called unsupervised learning. And so here you cannot apply random forest SVM because the random forest SVM will need an output variable. You need to specify, and you also need to give what input variables are. So in clustering, the idea is to automatically group this into however number of groups you choose. So if you want to group it into your email problem into 2 groups because you're looking for spam and no spam, then say each point on this XY plane is denoting one particular email. Say if your result in an ideal case ends up becoming like this, and then you have a lot of points, lot more points, because assuming spam is like minority, right, for example, and if it clearly, so this is like a very ideal scenario, then you know your clustering will say all these points belong to group 1 and all these emails belong, even the point is an email here, belong to group 2. And then you will know, there seem to be 2 specific groups of emails, and then you will then kind of spot check some emails and see why are these all spam or are these all spam. Then you will see, oh, these all seem to be spammy, these all seem to be non-spam. So this is the spam cluster, this is the non-spam cluster. Then in the future, when an email arrives, what you do is you try to see if that email is closest to, if that email point is closest to this guy or this guy. So if he ends up somewhere here, then he's closest to this guy. Then you'll say he's spam. If he's somewhere here, spam, you know, that kind of thing. So it is easier said than done. Clustering does work well reasonably sometimes, but sometimes it's very hard to work in your favor. So you won't know what's going on. If it makes a cluster very complicated and not really clear which is what, then it's not solving your spam classification problem anyways. And then you're getting groups of emails. Maybe you're getting a group of email of all United States emails and all Chinese emails separately. So many things could happen. So what you're looking for may not end up coming in the clusters that you're making. Also, just like random forest, SVM, neural networks, all these have different parameters you need to tune. Clustering techniques also have a choice of some choices that you need to make for it to work in your favor, and it is not very clear how you have to make those choices. In supervised learning, random forests and all, you had some methodology, right? How to choose parameters. You could do you were doing cross validation and all that to see how you could choose your parameters. But here the methodology is not clear. So so it is, it's a little black magic and intuition in some ways. All right, so now let's see how this technique, but that said, the clustering is still very popular because sometimes it does work well in your favor. All right, so it's more exploratory as well, your choice of parameters. So once you start exploring your data based on your intuition, you kind of choose. All right, so we will be covering k-means, which is a very classic technique, very popular, very easy to explain. And then spectral clustering, very popular and a lot more powerful than k-means. Bi-clustering is slightly a different scenario. Let's finish this first, k-means and spectral. So I opened two sets of slides, one for k-means and one for spectral clustering. So let's start with k-means. All right. Yeah, that's what I was doing. Okay, so yeah, this is again, as you see some slides from, well, it's funny. Okay, yeah, this guy was in NYU when he generated the slides, but right now he's a professor in MIT. So this is, I guess, ML course. I don't know, grad or undergrad level. So, okay, let's go over these. So, yeah, as I said, it's unsupervised learning. I have no clue why this guy is here. Okay, yeah, so it does require data, but of course, no labels, right? That's the paradigm in unsupervised learning. So you want to detect groups or patterns. So for example, group emails or group search results, group customer shopping patterns, group regions of images. So grouping regions of images is also similar, known as a problem of segmentation. So say, I don't know, the head is a similar region, the pillow is similar, the bed or pillow is similar region, the headphones are a similar region, shirt similar region, right? Because you can see the shirt head, it's completely different image intensities. All right, so that's known as a segmentation problem. So this is actually when these days, almost all cameras have like the face recognition feature, right? When even before you click the camera, the digital camera, it will give you that square or rectangle box around the face. So it's able to recognize the face automatically so that it can zoom or center the face nicely when you generate the image. Not zoom, but it can focus in a way that your face is coming more clearly. And it's not focusing on some background, someone who is playing baseball or something, and it's or some grass. It will focus more on your. All right, so that is the segmentation, which is also unsupervised and a clustering kind of a problem. All right. Yeah, so this is important. See, it can be useful sometimes, but it sometimes can be rubbish, gibberish as well. Okay, the clusters that it is providing. All right, so let's get gradually into k-means. So this is the inclusion which I was providing in the little cartoon, right? You want to group points. So if say you had only two variable data set, then you want to group your 2D point patterns, right? Because each variable is a point. If you had a high dimensional variable, each variable is a high dimensional point, right? One variable to explain one point to explain, you will have maybe 10, 100 million variables, right? So for example, genetic information. So my genetic information will have like thousands of variables. Then again, another person will have thousands of variables. Then you want to group into maybe age group, just looking at genetic information, or maybe into diabetes, no diabetes, cancer, no cancer, these kind of things. So that then you can see what are the patterns that are emerging between the cancer cluster and no cancer cluster based on genome and genetic information. So that's a point of dimensionality here. So here he grouped, because these are closer, he grouped these 2D points into one. This is second cluster, this is a third cluster. So you have different sized clusters. And within each cluster there is similar, because this point is much further from any point in this cluster or this cluster. It's much closer to points in this cluster. Then people can say, why was this grouped into 3 clusters? Why can't I divide it into two more clusters, right, in the half? Maybe possible. Why it probably did not is because this point and this point are also reasonably, compactly closed enough. This whole thing is like one compact piece. That could be another reasoning. But if you force the algorithm to choose 4 clusters, then it will do something like that. Or it might divide these 2 points and these 2 points into 2 different clusters. Or this guy will end up one single cluster, and these 3 will be one. Right? So this is the reason sometimes, based on your choices, things can be rubbish. Sometimes very useful. All right. So group together similar instances or records. Okay, now the question is, what is similar? One straightforward answer to how you measure similarity is, the Euclidean distance. This is the same distance that you learn that you use to, you've seen this a lot of times in I don't know, 11th or 12th grade, I guess. So Euclidean distance is the follows. If you have, for 2D points, for example, it can generalize to whatever whatever dimension of points. Say you had one point x1, y1, you had another point x2, y2. Right, so this is your plane. So say this was x1, y1. This is the one point. This is the one set. Let's call it this one. This is the one point. This is the second point. Say it is somewhere here. Now the idea, what you want to do is you want to measure this distance. Right. So this is x1, y. So you want to measure what is the distance. So Euclidean distance, as you've seen, is y2 minus y1 whole square. So basically, this is y-axis, right? This is x. So it is y2 minus y1 whole square plus x2 minus x1 whole square. So basically, you are trying to see in the y direction how far these 2 points are. So this point is, this is the y1, this is the y2. You want to see how far it is. Plus in the x direction how far they are. This is x1, this is x2, right? This is the x2, this is the x2. So you want to see how far they are. So x2 minus x1 whole square plus y2 minus y1 whole square. So this minus this whole square plus this minus this whole square. If you sum those two quantities, you get Euclidean distance. Now you can see how this will generalize to however number of dimensions, right? If you had x1, y1, so on till okay, instead of using x1, y1, z1, let's say x1, one point is x1, x2, so on till xd. This is point 1. You have d dimensions. D could be even 1,000,000, 100 million, trillion, whatever. Another point is say y1, y2, so on till yd. You want to measure the distance between these 2 points, because in reality you always don't only have 2 variable records, your SQL database or your your MongoDB, whatever. Each record might have hundreds of variables, right? So D could be hundreds. One record has so many variables to describe it. So this could be spam email record or some banking customer record, whatever it is. Some, I don't know, some scientific, something to do with some physics, or I don't know, some academic related record. So now it generalizes very obviously. So Euclidean distance is yd y1 minus x1 whole square plus y2 minus x2 whole square plus y3 minus x3 whole square, so on, so on. You keep summing up, plus yd minus x3 whole square. Right? That is it. Right. So that is the Euclidean distance. Now comes a very interesting question. This is just one choice of distance metric. But this may be good for some purposes, but sometimes maybe for email clustering problem, maybe this is not what you want to measure. You don't want to, this is not good enough, I guess. Maybe this is not giving you the clusters that are separating email and no email, spam and no spam. Maybe you want to look at some other distance, right? So the choice of distance is very important. If I want to give you a another example where Euclidean distance fails miserably. Let's take the sphere. The sphere. Okay, yeah. Let's choose any sphere. Okay, this is a sphere. All right. So if let's choose 2 points. So let's take a point somewhere here. Try to imagine some point here and another point somewhere here. Okay, 1 point in this region, 1 point in this region. Euclidean distance is always straight line distance. That will give you, what it will give you is, if you cut through the sphere and literally join this point and this point with a straight line, the line will obviously pass from inside the sphere, because that is the only way you can go straight from one end to an end. Then you get Euclidean distance. Okay. But then another distance is known as the geodesic distance. For any geometric surface in pure math, there is a concept called geodesic distance, which is basically this curved distance. If I'm walking over the sphere from this point, I want to walk over the sphere to this point. The curved distance, but that is the closest connecting this curved distance. Then that is a different distance. That value and your straight line value will be very different. And especially for some geometries. Let's take another thing. Swiss roll is like a cake. It's a dessert actually. So it looks like this. It is an interesting geometry. Why am I taking this out? To show you why Euclidean distance will fail miserably and some other distance is required. Now let's take a more geometric version of it, the same shape. So if you see this is the Swiss roll, you can unroll it. The way they make it is, they first make it like a flat plane. They put all this nice red jelly or jam, whatever, or chocolate, and then they roll it in this shape. So it's a flat thing rolled. So it's a Swiss roll. Now let's take a geometric, like a nicer version of it, the same thing. This is a Swiss roll. This is the cake we were looking at. Okay, now, okay, look at the right side image is more than enough. Say I took a point on this end on the red surface and 1 point on this part of the blue surface. Just imagine 1 point in somewhere here, the second point is here. Straight line distance is this one, Euclidean distance. It will say this point and this point are very close by. Now the geodesic distance, the distance on the surface of your geometry, on the surface is this long distance. So by geodesic distance, these 2 points are as far as they can be, or even say this very end point and this end point, the farthest points. So it means this point is very different from this point. If this was spam emails, this is no spam. It is very good because you're clearly separating spam from no spam. If blue was the no spam cluster and this is the spam cluster, or the other way around, maybe this is spam cluster, this is no spam cluster. But if you pass this data into Euclidean distance-based clustering, then it will say these two are the closest points. It will say the spam emails, the no spam emails and spam emails are very similar. It means you are grouping exactly what you don't want to group. So that is this is another beautiful example where it shows, given your data set, when you're clustering, your choice of distance metric is very important, and your data might be lying. If here it is 3D variable, right? You have 3 variables to describe this point, any point here. But you might have 100D variable as well. Regardless, your points will be lying on some geometry, some surface, some curved and complicated surface like this, some other surface you don't know of. This could be just one puzzle set. It's not always lying on a plane where straight line distances are good enough. This is known as this is not Euclidean geometry. Straight line distances are not good enough. This is known as Riemannian geometry. So you have curved distances coming into play. So what this tells us is, based on your data points, you need to first understand the surface, and based on the surface, you need to understand the distance on that surface to really see if you're doing clustering correctly or not. So as you see, like a simple explanation, we can make it more and more complicated and more in-depth in terms of just being able to figure out what distance measure is ideal for your clustering. Okay. So they are crucially dependent, like this guy says, on the measure of similarity or distance. Similarity means closeness, distance means how far, right? Between points to each other. It's very crucial. Oopsie. Okay. Alright, some popular clustering algorithms, k-means, mixture of Gaussians, spectral clustering, hierarchical clustering. Right? And within hierarchical, there is agglomerative, divisive. These are some popular ones. We'll start with covering k-means, some hierarchical and some spectral, mixed of Gaussian, maybe not today itself.
So Pradeep,
Yeah.
SVM is part of unsupervised?
SVM is supervised.
Okay.
Because you are literally trying to predict a variable or classify, but you are also provided that variable to learn your algorithm. So
Okay.
I give you input, I give you output, then you learn how to go from input to output. So in the future, when you only have input, you know how to predict the output. Here you only have input variables. No, like I will not say this particular variable is output variable. I won't tell you what is target. Okay, so there we go. Yeah, image segmentation, right? This is very popular. Computer vision kind of application. So given any image, you want to segment different regions of the image, right? Because this is the water. You want to computer wants to automatically identify this is cloud, this is blue sky, this is grass, this is I guess a road or some patch, mud road I guess, along the between the hill grass and the water. So how does computer automatically identify it? This is a clustering problem because water, these are all similar intensities because image is a bunch of numbers in the end, right? Here you have some intensity numbers. So depending on color, you know, color, hue, whatever, intensity, everything. So basically, if you do clustering properly and if you choose the right number of clusters and right parameters, I'll talk of other parameters involved in the algorithm, but if you do it properly, then it will automatically say all these pixels are water or belong to one cluster because they seem to be water. This is another, this is grass. And now you can imagine some another application working on high level on the result of these clusters can do a lot of things, right? Because if it is able to figure out that which cluster is say faces or which cluster is cars or which cluster is license plate and what the number is, you know, there are so many applications you can keep on top of computer vision, obviously. James Hayes. Okay, this guy is a computer vision professor in Georgia Tech, Atlanta, I guess, or maybe not. Oh, that is Jim Reg. So this guy I don't know. Okay, someone. All right. Anyway, clustering examples. So yeah, gene expression data, right? Because you want to cluster genes of patients with some condition and healthy patients. For example, based on their genetic data. These days a lot of genomic related work is going on, right? So basically, in a typical gene expression data set, you will have a lot of genes. These are genes, and this time rows are not records, they are genes. So these are the variables. And this is either time or could be different patients, for example. Usually you have few patients' data that you run the tests on, and then you collect their genetic information. The reason you have few patients' data is because these tests are very costly. Like profiling the entire human genome is very, very costly. So yeah, so you only have few people. You cannot do it like for hundreds of thousands of people. Right? Then it will be like billions of dollars or like millions of dollars. So you don't want to do that. So you want to do it for maybe 100 people. And then within that 100 people, you will have, I don't know, 50 people with some condition, some cancer, some condition that you believe is genetically also very, where genes play a factor. For example, if you do genome data with patients that have like a common cold or flu or fever, it's like a waste of hundreds of thousands of dollars because if it is standard common cold, nothing to do with genes. He just got an infection somewhere. But if it is something to do with some genetic related thing, right? You don't know, like some cancer related stuff or some Parkinson's, whatever is genetic. I'm not a doctor, so whatever it is, based on those conditions, then it makes sense. Then you want to see what genes express differently between the condition group and the healthy group. So there you want to cluster. So you will have few records but many variables in genetic data typically. Okay, k-means. This is one of the simplest but very classical algorithm. The idea is this. Let's take this dummy example. So you have, as you visually see, you're already able to see 1, 2, 3, 4, 5 clusters. If you force it to do 4 clusters, then it should choose this as one cluster, this another cluster, and maybe it will join these two. Maybe not, maybe it will join these two as a 4th cluster. All right, now if you want to choose two clusters, then maybe all these three are one cluster and these two are two clusters. Or these, if you want three, these two is one and these three are one cluster. So 1, 2 and 3, so on. So first you need to decide, like I said, the algorithm won't decide for you. You need to decide how many clusters you want to group your data into. So you pick k, the number of clusters. And then the way the algorithm works is it first initializes k. You need to give k random points, right? Because you don't know where the clusters, so k will decide how many clusters and you need to choose some point which is cluster center. You might have started somewhere here, here, here. You'll have those, as I go to next slide, it will give you those each step. So I will do that. So you choose k points and you say these are my cluster centers, right? Because if you have no idea, maybe you will choose this point, this, all maybe points are here only, or maybe 1 point here, 1 point here, 1 point. However it is, you choose randomly. Some points may be in the white space also, somewhere here. You choose k points, but k is the number of clusters you want on the algorithm. Then what you do is, once you have the k cluster centers, then you iterate every single point in your data set, so every single blue point in your data set, and you'll see what is the closest cluster center for any given blue point. So if this is closest to a cluster center you chose here, then you will say this belongs to that cluster. If this belongs to some cluster center here, then it belongs to that cluster. Then you again average, then you have identified all the points as some particular cluster out of your k clusters in first pass. But this may not be good enough, obviously, right? Because in the beginning you started with random clusters, right? But you need to refine this. So then what you do is, once everything has been binned into one cluster, each closest cluster center, you know what your initial clusters are. They are not good enough, but you clustered something into k clusters. Now within each cluster, you compute the average. And then you will update your cluster center to be the average point. And then again, you will bin all the points to closest clusters. So things will change a little bit again. So you do that again and again till things converge and don't change much in terms of cluster assignments. So since stop and no points assignments change or don't change much basically. And then you have your clustering done. All right. So k random points cluster centers first point, right? So maybe first you chose this point as a cluster center, this point as a cluster center, this, and this. And then each point got assigned into the closest cluster center. So this is working reasonably in this data set, right? Because all the blue points here are closer to this point, then they are closer to this or this cluster center. So they became this cluster. So on. So you got one initial clustering. And then the second step was this thing, right? You compute the average point of this cluster. So the average now moved to here because you assigned to these points, the average point ended up here. So that is your updated cluster center. Then you again assign all points. You do that again, things don't change much. Then you have your whatever number of clusters you chose, 4 or 5, 6, whatever. That's how k-means works. Again, same thing he's showing. Pick k random points as cluster center. So he picked these 2 points. So these are like absurd, right? So ideally, maybe this is one cluster and this is another cluster somewhere. Somewhere the cutoff will be some points will get confused here and there, but maybe some line of differentiating, right? Maybe one is spam, one is no spam emails, data, 2 variable. Maybe cancer, no, whatever it is. So this is absurd, right? That's it, random initialization, right? This is nothing to do with clusters. All right. Then what you do is you assign for each point you see which cluster center is closer. So this point, obviously this is closer. So this goes to this cluster because this is farther from this cluster center. Now this point is closer to this cluster center. So every point gets assigned. Then you have one grouping. So that's what happened. All these points ended up becoming blue cluster in the same example. Right? All these points ended up becoming red cluster because all these points are closer to red than they're close to blue. And so on. Then you update your cluster centers. Now obviously the average of the blue points will not be here anymore. It will be somewhere here or maybe somewhere here, little, because it has a little more points, just pulling it slightly this side, somewhere here. Red will not be here because more density of points is here, probability is higher here. So this will go this cluster center will be somewhere here. Then you again update your cluster assignments. See how it is working. But see, so now that's exactly what happened. So I guess here is slightly more points, so this cluster center went here, this cluster center went there. Right? Now you update your cluster assignments. Now obviously some mistakes are going on, right? Because these points were previously in this cluster, right? These points were previously in this cluster, but now They are supposed to be in blue cluster. So now when you update, once you updated the cluster center, now you again reassign the points. Then automatically these red will also become blue, these blue will become red. So that's how you separate it. So beautiful. This is really beautiful. So you separated your data. You started with some absurd initialization and you separated the two groups. So that's how k-means works. Now, these are all nice examples where k-means works. There are examples where k-means will fail horribly as well. Okay, but we'll get to that when we go to spectral clustering very soon. Right, this k-means clustering. And these things, believe me, in terms of code, are some of the easiest things to use. But obviously, you will have to do a lot of trial and error, visualize your output and see if it looks nice, or you want to change parameters, cluster numbers, all that kind of thing. In k-means, the only parameter is choice of k. But there are also versions of k-means where here everything you are doing based on Euclidean distance, right? How are you measuring point to cluster center distance, or whatever you're measuring is based on Euclid. The centroid is measured based on Euclidean distance. But you can also have k-means with some other distances measures, right? Yeah, so that is it. Right, so you are more CS guys, so this is giving the complexity of them, but that's not the point of the. So yeah, what properties? Yeah, so this is what he's talking. You can choose other distance measures, but what are the minimum properties that any distance measure should have? It has to be symmetric, because distance between A and B should be same as B and A, right? Because distance between me and how my wife looks in terms of similarity should be the same as the distance between how the similarity between my wife and myself is. Then you can cluster a group of people based on their similar faces or whatever. Otherwise, it is like going to be irrational, right? You're going to get stupid results otherwise. Positivity and self-similarity. Oh, yeah, you want to have distances. So if they are exactly the same, then distance will be 0. So if you're comparing distance between my photo and my photo itself, then it has to be 0. Because similarity between my face and my face cannot be more than 0. Then something is wrong. Something is off, like it's not calibrated. And obviously distance, when they are not same, it will be greater than 0. So only possibility is greater than. You cannot have a negative distance is what he's saying, because distance between New York and California will always be either, any two cities in any place in America will either be greater than or equal to 0. You cannot have negative 500 miles. That's impossible. All right. Another, whatever distance measure you choose, these three properties compulsory. That's when it is known as a distance metric. Otherwise, it is just a similarity measure. It's not a metric anymore. The third one is also very important, triangular inequality. So this is just, when you have a triangle, you don't need this. Well, why right triangle? Let's have any triangle. Okay. The sum, there is a property like a high school property. The sum of any two sides is always greater than equal to, well, any two sides means the sum of the lengths of any two sides is always greater than equal to the third side. This also has to be satisfied, because if this does not satisfy, there's something wrong with your distance metric. Oops. Because then when you're comparing triples of point, more and more points, you will get absurd rational behavior. That should not happen if this is not satisfied. Okay, because otherwise, if that is not satisfied, you can say what will happen is you will get irrational outcomes as follows, inferences as follows. You will say A is like B and B is like C, but A is not like C at all. That is impossible, right? Because maybe I look similar to some cousin or brother of mine, and brother looks similar to some other cousin, but these two do not look similar. How is it possible? Like it's like New Delhi is of some distance to Beijing, and Beijing is of some distance to New York. But distance from New Delhi and New York is not same as the, is less than the distance from only if your flight can fly through these three destinations, not on the Earth, not the spherical distance. Then it cannot be lesser than equal to some of the distances, right? Because I have to go from Delhi to Beijing and then Beijing to New York. I cannot reduce that distance. So for those kind of absurdities to not happen, you should have triangular inequality to be satisfied to whatever metric you choose. And Euclidean distance, the straight line distance, obviously satisfies all these three. You can never have a negative Euclidean distance. You can never have symmetric Euclidean distance. You can never have Euclidean distance where triangular inequality is not satisfied. All right. So this is whatever we discussed here, the steps of the k-means in these nice beautiful pictures and these steps here. now is encoded here mathematically. It's not some hi-fi math by any means. It's very simple if you look at it. So so basically Muse are your so step one, okay, first you choose your different cluster centers, and then you go through every point, and then you assign which cluster center it is closest to. That is the step one. So this norm square is basically Euclidean distance square that it is measuring. And then what you do is you update so the cluster centers are Muse basically. So for each point you're seeing which cluster center is closest and you're assigning that there. Then you update your cluster centers, which is the average step here. Here you're updating because you're finding centroid within any given cluster. So every point within any cluster I. So within cluster 1, within cluster 2, within cluster you're finding the average, and you're updating your average to be that newer average. So the step 2. Then you repeat 1 and 2. Da, 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 da. Okay. So again, examples. When k-means was applied to these images. So the goal of for the segmentation purposes is to partition image into regions which are similarly homogeneous, right? Visual appearance. So for 2 clusters, it encoded into this yellow patch as one cluster and this background as one cluster, right? This was your original image. These are all 2 cluster possibilities. There are only 2 colors here, 2 clusters. And so for this image, this happened to the k equal to 2. But if you do more clusters, then it will start to separate this bag or whatever this thing, this play thing. This maybe it will separate his hand, his biscuit, and this thing, his seat, separate. Headphones separate. More and more clusters you use. That's what it's showing. I wanted to show that. K equal to 3. Here you see 3 colors are being used. Here the guy got separated more nicely because he's more brownish color here and got separated from this thing he's playing with. And then the background got separated again, which is separate from this object. But obviously, if you see his hands and face, it is saying it is the same as this. It could have happened because it's similar intensity of colors. He's not yellow, but he's more yellowish than blue, for example. That's what I meant. Same thing here, 3 clusters, so on. You can keep going. Oh, nice, beautiful. 10 clusters. Oh, even more separations. So now it clearly is able to separate. Red is one object, this is one object, face is different. So on. Because here if you see face, this thing, this red thing, everything is similar. Head is almost more patches, similar objects it is saying. But here it is clearly saying red is separate object from this. Alright. Vector context. Oh, Ronald Fisher. He's like one of the founding fathers of statistics. So that's what I wanted to say and that's what he wrote here. But let's not discuss this example. Vector quantization is slightly different technique. It's not exactly clustering. All right. Initialization. Why is this slide? Yeah, now we are looking at why k-means can go wrong, when and why it will go wrong. Your initialization could be messed up. That is one big scenario. Maybe you initialize too difficult that it is not converging the way you want. It's getting stuck in some local optima, not the true answer. All right. And also, say if you have data like this, if you are using Euclidean distance, then you might have issues because you want to have this curved distance. Then all these points are one cluster, these points are one cluster. Otherwise, these and these points can end up becoming one cluster, right? If you wanted that kind of a separation, then now you're looking at geometry, right? Like I showed Swissroll. If you wanted some other distance to give you the right result in your application, then the choice of distance helps. Okay, distance function is important. Right. Another technique is agglomerative clustering. This is like literally building a tree actually, like a tree data structure. So first merge very similar instances. So here you're just comparing distances based on whatever your metrics, say even for Euclidean, so these two are closest, these 2 points closest. Once all pairs of closest points, you will merge and say they are one cluster. So this is one cluster, this is one cluster. Then you will merge those clusters basically. And you'll keep merging up and up and up and you'll go, or like down and down. You will get a tree. That is the agglomerative clustering. Okay. And then there is also, once you have groups, right? First time is easy. You grouped these two in one cluster, these two, like, then the question is, when you have groups, how do you measure distance between two groups of points? If it's 2 points, I can measure distance, Euclidean distance, whatever distance how do you measure groups of points? There are many possibilities, right? See, one is closest pair. So within this group and this group, 1 point from here, 1 point from here, that are closest. This is known as a bipartite graph, by the way, in graph theory in CS. But anyway, you want to choose 1 point in this group, 1 point in this group, and you want to find the closest pair. So this is the closest pair. So they can use the distance between the closest pair as an option for distance between these two groups. Another option is closest distance between farthest pair, right? So depending, as I said, your choice, even in agglomerative clustering, your choice of metric is also very important. So there is a single link clustering you will get if you use this. If you use this, there is a technique called complete link cluster. You can use complete link, farthest link clustering. You can also do complete link. You can use average of all distances, all pairs. So many possibilities. And every time you'll get different answer based on your possibilities. And as you think, right, practically, I will give you data set. You will know you want to cluster, but I won't tell you what. You won't know, neither I or you will know what distance will give you the ideal cluster that will help your business or your clustering application. That's the slide. But sometimes it works fine as well. It's not that tricky. Right, so single link clustering gave you completely different answer than complete link clustering. So single link refers to this thing, right? Closest pairs distance between groups. Then you will merge these two. Based on the, if you had 10 groups, you will only merge those pairs that have the closest pair distance. Single link clustering. So this is farthest link clustering. This is a red line you are using to measure the distance. Single link clustering, it apparently said 1, 2, 5, 6 are one cluster. First it said 1, 2 is a cluster, 5, 6 same cluster, 3, 4 same cluster, 7, 8. Then you're combining the tree, right? Then it merged 1 and 2 and 5 and 6. That's why this circle is showing. It said these four are similar, these four are similar. So there are two clusters. Of course, if you do everything, all will become in one cluster. There's nothing beautiful about that. You will say everything is one cluster. But if you choose same data set, if you did complete link clustering, it started choosing 1, 2 as a cluster, 3, 4, 5, 6, and 8. So first step was same. But then it joined 1, 2, and 3, 4 as one cluster. So now it's saying these 4 points are similar. Here it is saying these 4 points are similar. You see the difference? So just based on your choice of distance, you're getting different answer. Okay, this guy, okay, now I can, this guy definitely is a professor in Cornell. He's very popular in machine learning, data mining kind of area. All right. Clustering behavior, right? Yeah, different links clustering. This is how he's grouping, right? You're generating a tree, basically. Groups, right? First pairs were combined, and those pairs were, this pair and this pair were similar. So like that, you're combining until everything gets combined. So this is your clustering tree. All right, based on different choices of cluster distance measures. Average, farthest link, nearest link. Average means average of all pairs. So this is on some tumor data. So this is some genetic data based on tumor, no tumor patients of mice. Hasty is a professor in statistics in Stanford. He wrote a very important textbook in machine learning. It's called Elements of Statistical Learning. Very popular book. The reason I'm showing this here is because it is completely open source. If you go to Stanford website, Hasty's website, I know it is open source. Let's see where it is. Yeah, you can download the entire book. It's a proper book. Like, there's enough pages, enough chapters in it. This is like the Bible for machine learning, the standard textbook for machine learning. There are 2-3 other famous books, but this is the one that I like the most. All right. Anyway, okay, back from the tangent. Yeah, this is agglomerative clustering. Same question. When it will converge, what distance to use, how many clusters to pick. It's always a problem. Right? Distances can be deceiving, right? Just based on your choice of distance. So that finishes k-means and agglomerative. We have spectral clustering left. For that, I have opened oh no, this is different. Okay, since you are sticking this guy's course on clustering, I continued on this guy's course for spectral. Yeah. Spectral is also a very beautiful concept. It is a little more complicated in how it works than k-means. Okay, now you want to see why. So when spectral will work better than k-means, right? Or when k-means fails. So in this data set, ideally say the guy wanted inner points to be one cluster, outer points to be one cluster. If you use k-means with 2 clusters with Euclidean distance, it will say this guy and this guy is one cluster because this arc is similar to this arc and this arc is similar to this arc. Because you are forcefully separating into two clusters, but this is not what you want. For example, say these are spam, these are no spam, then you are making mistakes, right? So I'd say you want this pattern. Then spectral clustering will do this kind of pattern because it will understand the curved distance that I was talking about. If you think of this as a surface, you cannot go from here to here on the surface because it's not connected. So you only can measure curved distances. Based on that, it is separating, like the Swiss roll I showed. Not doing Euclidean distance, measuring the distance on the surface in spectral clustering. That's what is happening internally. That manifold, that surface that I was talking about is what it is doing. Spectral clustering has some nice cartoon examples. So these characters were clustered. So 8 characters. So all the endpoints it automatically recognized as one cluster. It did not say this point belongs to I or P or S. Another cluster. These digits. NIPS 2001. NIPS is a popular machine learning conference. So anyway, here also it gave these 3 clusters. It didn't say these green are close to red because it is measuring on the surface. Similarly, this example we saw before page. Instead of 2, now you have 3 circles, 3 concentric curves. Here also it is saying this curve is, so it's separating these objects nicely. It's not saying this point is close to this, and so it is this and this belong to one cluster. It's not doing that. So you see this nice compact separate objects are being separated as separate clusters. All this kind of magic K-means can do. Spectral clustering can do. K-means cannot do. K-means will fail. Okay, again, Andrew Ng, Stanford guy. Michael Jordan is a stat professor in Berkeley. This guy, I don't know who he is. So this was some example results on spectral clustering in their very popular paper in NIPS, that conference that I was talking about in 2001. Some analysis around that. Okay, spectral clustering. So what is it doing internally? So by the way, let me show you something. I know we are going out of time. Like right now we finished the 1 hour. So this is where we are in our here. So I said 2 courses, 2 classes, right? So we'll be, if you guys are okay with it, I can finish spectral clustering the next 10 minutes. It's a very simple idea from where we are now. So that we finish this and then we can go into this topics and little bit of conference intervals in the last week. So I don't want to extend this into 3 weeks. So let's try to focus and try to finish this off. If anyone has like any urgent thing, you can let me know. Then we can adjust it for the next week. Okay, so spectral clustering. So the way it works, the things we are showing here, how this works is, first you take your individual points, data points, and then you generate a graph out of it, like literally like the CS graph that you talk about. So you connect. So the question is how you join, which edges you join, which you don't. That I will tell you. But this is the overall idea. Then once you generate a graph, then we will do some magic to generate the clusters. So how to create the graph first point. So this is known as a Gaussian kernel function. Very nice function, very popular actually when I say nice. So the way it works is, this is Euclidean distance, the numerator. There is a term sigma in the bottom. Exponential is e power, right? So what is the exponential function? You guys might already know about. What happened? Simultaneous, I probably opened somewhere else. What just happened? Maybe here, I think it is not here. It is saying I opened 2. Where did I open? Okay, it might have as well happened that the cookies have failed or something. I don't want to clear them right now. Okay, anyway, what I wanted to show, since exponential function, you guys might already know, is a very quickly increasing function. So So this is the e power x curve, right? With small increase in x, e will increase very large. The y-axis is e power x. It's very fast increasing function. Now, negative exponential function is basically a fastly decreasing function. This one. It decreases super quickly, right? Like x changes from -2 to like 1 to from 0 to 1, y decreases this much. It decreases by 2 points. But when it decreases from x changes from just 2 points, 1 to 2, y decreases by more than -10. Right? So e power minus x is very, very low. So as x increases, e power minus x decreases very, very quickly. You see, e power 2 is what? How much? 7.3, right? E is what? 2 point something. E power 3 is 20, right? It's beginning to increase. But as you see, it will explode very quickly. 54. E power 5, 148, e power 6. Here I'm only increasing by one number from 1 to 2, 2 to 3. But here you're jumping from 2 to 7, 20, 50, 400, 400. E power 7, only 7 points I went. But here it increased 1096 points. Okay, now let's do e power 20. There you go. That's more than, definitely more than few billions. So e power, similarly, e power minus means negative exponential function, which means it is quickly decreasing. So with small increases in distance, this numerator, it will decrease very fast. Similarly, sigma is a parameter. Here you have a parameter, user input parameter for clustering you need to choose. So what this will do is, if you the point is to make a graph and connect some edges, right? So your nodes are your points, vertices. And the question is which edges to connect. So whenever your Wij is non-zero, then you are connecting that edge and you know what the weight is. The weight of the edges, it's a weighted graph. So the edge weight is given by Wij. So what will happen is, distance, this is Euclidean distance. This is what this is denoting that. So if you're taking 2 points, right, this and this, for example. If the distance between this xi and xj, this ith point and this jth point is very large, then which means they are very far off, then what will happen is e power negative of a very large number will be very close to 0 or will be 0, right? Because e power graph. And the sigma will also decide even further. If you choose a larger sigma, which means denominator is large, which means the fraction is much smaller. So then it means you will have a larger weight, because e power a smaller number is, negative smaller number is bigger than e power a negative larger number is very smaller. So if sigma is very small, which means the fraction is very big, which means e power negative a very big number will be very close to 0. So sigma small, you'll have, so what is this deciding? This is deciding nearest neighbors in some ways. Here you're generating distance, and here you're increasing the rate at which the distances will go to 0. This weight will go to 0 even faster or even slower. So if you make it bigger, then it will connect slightly far. This is also very important, because if you choose it, if you make these weights go to 0 very, very quickly, even quickly than the distances, then only maybe it will connect only these 2 points. It won't connect anything else. It will only say this point and this point is a cluster. It won't connect anywhere else. So if you choose the right resolution of sigma, then it will give you what you really want. It will connect these points. It will not connect these dotted points. Will be not connected. It will connect these dot points. So this is one cluster. Is one cluster. That's how spectral clustering is working. So very nice, right? Results. Spectral clustering. It's separating face, separating hair, everything. If you see, is spectral clustering applied on images. Object segmentation. Okay. So basically, we are partitioning our graph. So you have data, you generate a graph, and then from that graph, you know what the clusters are. That is the idea. So we have 5 slides that will finish how the math works. So there are some graph theoretic terminologies, some mathematical terminologies. So just definitions here. Degree of a graph is just the sum of weights. Degree of any node is the sum of weights of the edges from that node. So for this, these are the 4 edges you have, right? You don't have edge from here to here. So only sum of weights is known as the degree of that node. Similarly, you can compute degree for any node, summing weights of edges. Volume. So here definitions I will use now in spectral clustering once you know these definitions. So volume is basically the sum of volume of a subgraph, right, of a set of nodes. Is the sum of degrees in that subgraph. So the volume in this part is the sum of degrees of all vertices. So each vertex has a degree, you're summing it up. This is known as the volume of the graph. Alright, so now where are we going? We're going to the final part where we are able to generate a graph based on our choice of that W sigma function using the W function we showed above. And once you have a graph, now we want to go to this final step. How do we look at the graph and say which is which cluster? Right? And how do we do that separation, partition? That is the final step. So say you generated a graph like this. As you saw, the weight is a smaller number means these points are much far off, right, in this weight function. Smaller, it means they are far off, because they are far off only, weight will be small. So smaller is a good measure of separating two groups, right? So if these 3 are connected by weights of 0.8, 0.6, 0.8, and these are connected internally by 0.8, 0.7, which means these are closely connected, these are closely connected, but this group is very small number, which means these are not well connected, which means you got ideal result. This is one cluster, this is one cluster. They are not connected. Right? It's only yellows are connected. So ideally, we want to partition the graph based on, say, a criteria. Let's call it a cut. What is the cut? Sum of the weights of the set of edges that connect two groups. So this is a group, this is a group, the sum of weights of edges. So 0.1 plus 0.2, 0.3. If this is minimum, which means you have separated these groups, the intuitive goal is to find a partition that minimizes this cut. You want to use that kind of a partition. This partition, which means you only want to connect in that way so that these two get separated. So slightly improved version of that is known as a normalized cut, which is also taking the volume of each group, which means internally you want to have connected as well. Like what volume is doing is measuring how well connected any given group internally is, right? Because you're measuring summing the degrees internally. So the degree of 1 is 0.8 plus 0.6. Degree of 2 node is 0.8 plus 0.8. Degree of this node is 0.8 plus 0.6. All those sums of degrees is known as a volume. So you want to have high volume, which means internally they are very connected, and then low cut. So the cut is minimum. So which means these are very compactly connected. These are highly volume. Then cut between these two are separate, which means you are getting a very beautiful. The same for both, for the bth group as well. Cut A comma B has to be minimum, volume of B has to be maximum, which means B is very well connected internally, A is very well connected and B. You don't know what subgraph to choose, right? Because initially you have all points. You want to choose some subsets of points A and B if you want two clusters. If you figure out which falls in A, which falls in B, such that normalized cut is minimum, then you have the best cluster. This is how spectral clustering works. So this thing, you can just sum these two fractions, right? You know what is going on here. I hope so. X by Y plus Z by W means you're just summing these fractions. This is the same as this. This formula is exactly the same as this. So yeah, normalized cut. Now, X is your output, right? You want to assign cluster 1 or -1 for any given point. With all these matrices, degrees and everything. So the thing is, Optimizing this is an NP-hard problem because finding that subset of A and B is very hard, very common to it because many permutations of A and B are possible, right? So a slight relaxation is done where they subject the same thing to a. So here instead of minimizing this, what he's doing is he's minimizing just the numerator and he's saying the denominator is equal to 1. So that's a constraint. So this is known as an eigenvalue problem. So here it's going into more complicated math because to explain eigenvalue, I might take another full, maybe another half an hour or so. So let's not go there, but we can always do it in any time in the future, I guess. So, but you understood what the normalized cut is useful, I hope, because you want to have high volume within groups. You want to find groups A and B. You want to partition your nodes into groups A and B such that the volume within each group is high, means they're well connected internally, then the cut between the groups is very low. So groups are very far off, but within the group they're well connected. That is the definition of a cluster. That's what this is. So this is an eigenvalue problem, which means the solution that you want is basically the eigenvalue, the eigenvectors of this matrix internally, the D minus W matrix. So basically, if you want to compute spectral clustering, what this is saying is you compute degree, you compute the W matrix. Well, first you compute W matrix, you compute the degree matrix based on those weights. Then compute the difference of those two matrices. And then solve this generalized eigenvalue problem and then find the eigenvector y. So your eigenvector y, the second smallest eigenvector, is the real solution to this problem. This is a, if you're interested more in value problems and stuff, this comes in linear algebra. This is a prerequisite to machine learning, similar to calculus. So if anyone is really interested, then you can reach out to me. I can explain how eigenvector problems work. You might have heard of eigenvectors before, eigen decomposition, right? So for any matrix Ax, if you're solving the equation Ax equal to lambda x, then the x, A is your input matrix. If you're trying to find an x such that if you multiply A with x, your result will always be some lambda scale, some scalar times that vector x, which means you're only expanding or contracting the x vector, right? Those x's are known as eigenvectors of the matrix A. There are only very specific number of eigenvectors any matrix will have. I can explain this in more detail if you want, like in a class separately. You can reach out to me by email. I can explain the linear algebra there. So this is the spectral clustering. So the solution is to generate a graph and generate the right cut, which is separate the nodes in your graph. And for that you're using the normalized cut notion, which is minimize the volume between groups, minimize the cut between groups and maximize the volume within groups. And to obtain the solution of a normalized cut, you are using some linear algebra, which is an eigen solution. That is the part we slightly skimmed over quickly, but till normalized cut, we have covered it quickly, like in a connected way. Any questions? Anything? So that's how spectral clustering works.
Yeah. Usually, the spectral clustering is applied on which data?
Whenever you have a clustering problem, like unsupervised, right? So even on the email problem. So whenever you have a clustering, you have a choice. You can apply k-means, you can apply spectral clustering, you can apply, hierarchical, the agglomerative, the tree-based clustering. But these days, spectral clustering is more preferred because it is much better than k-means. But so if you want to do clustering, go for spectral clustering. But then if your data set is extremely large, then you need to have since your solution is an eigen solution in the very end, you need to have a fast eigen solver. If you have fast eigen solution, that kind of packages, then you are going to get scale to a larger data set. Otherwise, it is hard to scale. Another issue in terms of computational bottlenecks is you want to first generate the weights, right? Its weights. But if you have many millions of points, you need to generate a W million by million matrix. If you have 1 million points, you need to populate that matrix. So there you have order of n square, order of million square operations, right? So that is also creating W itself is also a headache if you have a very large data set in general. Because in k-means you're not doing that always. You're only doing nearest neighbors kind of thing. To some extent, like there are faster implementations. And one homework assignment. I will also email you. If you go to your UCI machine learning repository, which I shared with you, you go to data set, all data sets. See, there are 69 data sets for clustering problems. So you can go over through some of the data sets, choose something that is of interest to you. So say character trajectory, say you are clustering characters, right? Because human handwritten characters is different from so if you're able to do character recognition, you can apply spectral clustering into it. Some diabetes data, this one accelerometer, this is interesting data. This is like your smartwatch. Smartwatch has a lot of sensors in it. So based on that, you can want to ADL means activity of daily living. So you want to say just by looking at the smartwatch sensor data collected with accelerometer, you want to cluster and say whether the guy is doing dishes, is he taking a shower, is he sleeping. You can separate. You can identify what he's doing just based on his Fitbit data. Just based on what I don't know if he uses Fitbit, but whatever is smartwatch.
Okay.
Then you can obviously do follow-up projects. Then you can count how much time in the day is he, doing unhealthy activities like sleeping in the couch, watching always TV all day, versus how much active he is, right? So that is like a second layer from your clustering. After your clustering, you can compute within the cluster how much time is being spent. Then you'll get how healthy or unhealthy his lifestyle is, right? Or is he doing dishes every day, doing a lot of his household chores, moving a lot, walking a lot, right? It may not be only within the house, generally wherever he is. You can see, is he sitting in the office all day, right? Versus is he he's sitting in the office but also walking, he's taking time to do some gym. Everything you can recognize your activities properly. 14 activities are there. So 14 clusters. With if you do with high accuracy, then you can also decide how healthy one person is or unhealthy his lifestyle is. Right? So the 14 activities are interesting. Brush teeth. So just by looking at smartwatch data, you should be able to say, oh, this signal is saying this guy is brushing teeth right now from 3 a.m. From 7 a.m. to 7:30 a.m. something, 7:10 a.m. Climb stairs, combing hair, descend stairs, drinking glass, eating meat. See, not eating noodle, eating meat. It's very specific because meat is a different. Maybe he's cutting the meat in a different way. If it is the American style, right? It is a fork knife. Your hand movement is different. So based on your hand movement, your signal will also be different because it's smartwatch data. Eating soup is different. It's very different hand movement, right? Soup. Get up from bed, lie down in bed, pouring water, sit down chair, stand up chair, use telephone, walk. So maybe walk and stairs, all these are high and meet time, eating time is reasonable. And, bedtime is less. And if your chair time is also less, then it is healthy. If your chair time is high, if he's sitting chair 90% of the day, 5% doing everything else, then unhealthy lifestyle, right? All that thing you can identify. But once if you do clustering well, then you can go to that healthy, unhealthy question. So they're a very nice project. If you guys are really interested, you can apply clustering. It will give you a nice project. But these days, clustering and having a supervised learning, 2 projects will be more ideal because clustering is not everything. Supervised learning is also very popular. So there are a lot of clustering data sets here for you to pick from. Or you can do us with images as well, etc. Any other questions? Okay. Yeah, you were saying something?
No questions.
Oh, okay. All right then. Have a great weekend. Keep trying to finish more assignments and stuff. That needs to go into your resume if you are trying to portray some of these things. So projects in resume is important, and you need to have maybe some project like a blog or some GitHub link with some folder of your code, or some PDF project report and code. These are the things will make your portfolio or your resume a lot stronger. You'll have bullets. You'll have, I did clustering with activities of daily with smartwatch sensor data. This is my GitHub link. This is my PDF report. These are so and so. Then second bullet, something else. If you have like 4 bullets, 5 or 10 bullets, that will make you more and more a strong candidate. So for you to be able to get there, you need to convert your learnings into projects, and projects have to go into your resume. If this is the thing that you want to portray. If you want to portray something else, then you want to do projects in that area. Both can both areas. All right. Have a good weekend, everyone. Yeah. Bye-bye.
Bye, Pranit. Thank you.